let's give a baseline algorithm for sentiment analysis. And the task we're going to use is sentiment classification of movie reviews. And I've drawn on the work of Pang and Lee and their collaborators in this lecture. So their task was what's often called polarity detection, simple positive or negative, no complicated sentiment issues. And they're going to apply this to movie reviews from the IMDb website. And they've released some data that's often used in research called Polarity Data 2.0, which is a set of IMDb movie reviews that have been text normalized. And I pointed you here at the URL for that. Here are some examples of movies from their database. Take a look and see if you can decide which one's positive and which one's negative. Hopefully, you decided that the first one is positive and the second one is negative. And the way you would decide that is words like aggravating and unbelievably disappointing for negative and cool for positive. So these are the words that are going to help us in the classification task. And the baseline algorithm itself has a number of steps. We're going to start by tokenizing the words in the review itself. Then we're going to extract features, and the features we're going to look at mostly are words themselves. And then we'll take these features and apply them in a classifier. And we've talked about naive Bayes, and so we're going to use naive Bayes in today's lecture. But in practice, we might just as often or even more often use a Maxent classifier, which we'll talk about in the future, or SVM classifiers. Really, any classifier works fine. Sentiment tokenization, a lot of the same issues come up as any kind of tokenization we've talked about earlier. In sentiment, you're likely to be dealing with websites, so you're going to have HTML and XML markup. You might be dealing with Twitter, so now you have to deal with hashtags and Twitter usernames. Capitalization, which in many other kinds of text normalization isn't so important, often it's just we get rid of capitalization. We might, in sentiment, want to preserve at least some of it, perhaps words in all caps. People are often shouting by using capitalization. We're going to want to normalize phone numbers and dates. And it's very important in sentiment tokenization to recognize emoticons. So I'll show you here a set of regular expressions for detecting emoticons from Chris Potts. So here we have the one long regular expression for recognizing an optional hat, followed by an eye, followed by an optional nose, and then a mouth, and so on. So you can see each of that either in positive or reverse orientation. And this set of regular expressions comes from a whole sentiment tokenizer that I pointed you at here, and there's other kinds of tokenizers like Brendan O'Connor's Twitter tokenizer you can also go look at. So a number of issues come up in extracting features for sentiment classification. One is negation. It's very important to detect negation in a word like didn't, so we know that I didn't like this movie. We should be able to detect that it's quite different than I really like this movie. So we're going to need to deal with negation. And we also have to deal with the question of which words to use. We might want to use just adjectives. We might want to use all the words in the text. It turns out that at least on this IMDb data, and maybe in general, that looking at all words is better than looking at just adjectives, because often verbs or nouns or other words give us a lot of information about sentiment. So how do we deal with negation? Here's the simplest algorithm, first proposed by Da-Hsin Chen and used very frequently after that. We simply take the four letters, NOT underbar, and we prepend them to every word between the negation word and then the following punctuation. So we have a phrase like didn't like this movie, comma, but I, and we turn that into didn't, not like, not this, not movie. So now we've essentially doubled our vocabulary size. Every word could be itself or the word with not underbar prepended, and we're going to learn that these not underbar words, we've created words for negative sentiment, or for flipping the sentiment. To remind ourselves about naive Bayes, the most likely class, according to naive Bayes, is that class out of all classes which maximizes the product of two probabilities, the prior, the probability of the class, and the product over all positions in the document of the likelihood of the word in that document given the class. So how likely are we to see a positive movie review times for every position in the document, how likely is that word to have been expressed by a positive movie review. And the same for negative, and we pick whichever one, positive or negative, has highest probability. Or if we're doing 3, we're doing neutral as well, we could have 3 classes. And in practice, for sentiment analysis and lots of other text classification tasks, we use simple Laplace or add-1 smoothing with naive Bayes. So the way we're computing this likelihood, probability of a word given the class, is just by adding 1 to the count and then the vocabulary size to the denominator. For sentiment and other text classification tasks, we often use a slight variant of the naive Bayes algorithm called binarized or Boolean multinomial naive Bayes. And the intuition of this algorithm is that for sentiment and for other text classification tasks, we care more whether a word occurred or not than exactly what its frequency is. So, for example, the occurrence of the word fantastic tells us maybe a lot that we have a positive review. But fantastic occurring 3 times or 5 times may not tell us a lot more than just occurring once. So in Boolean multinomial naive Bayes, we simply clip all the word counts in each document at a count of 1. So instead of using the full term frequency, we'll just use a count of 1 for each document. So if we look at our original learning algorithm for multinomial naive Bayes, here, remember, we extract our vocabulary, and now we're going to calculate our priors. Remember the priors, by looking for how many documents occur with a particular class over the total number of documents. So there's our prior. And for the likelihood terms, for each word, for each class, we roughly counted how many times this word, the count of this word, over the count of all words in a class. And that gives us the likelihood of a word in a class. And then we did some add-1 smoothing. And we're going to do the exact same thing with Boolean with one extra step. Before we do our concatenating of all the documents into one big document and counting all the words in it, we are going to remove duplicates. So for each document, for every word type, we're just going to retain a single instance of that word. So if a word occurred 5 times, we'll keep only 1 copy of that word. And then we'll concatenate all of these documents, and then we'll do our counting and our add-1 smoothing and everything as we did before for naive Bayes. So that's our training algorithm for naive Bayes in the Boolean form. The testing, when we're doing Boolean multinomial naive Bayes, we do the exact same thing. We remove from the test document all the duplicate words. So if a word occurs 5 times, we keep only 1 copy of it. And then we use the same naive Bayes equation we've been using before on this slightly reduced text document. Let's look at an example of Boolean multinomial naive Bayes. And here we put up the little document that we saw when we were talking about naive Bayes originally. So we have here 4 training documents and 1 test document. And so the word Chinese occurs in class C. 3 documents are in class C. So it occurs 4 times. 1, 2, 3, 4, 5, sorry. 5 times. So the count of Chinese is 5. And it occurs 3 times in our test document. Chinese equals 3, and so on. And so in our naive Bayes equation, we're going to be using this count to compute the likelihood, the probability of Chinese given document class C. But in the Boolean format, we're simply going to pre-process the documents to remove all multiple copies of a word. Here's our Boolean version now. So you'll notice that there's only 1 copy of the word Chinese in document 1, 1 copy in document 2, 1 copy in document 3. So now our counts in the C class in training for Chinese, the count of Chinese. Now the count of Chinese is going to be 3 instead of 5. And in the test set here, count of Chinese is only 1. So it turns out that this version of naive Bayes, binarized Boolean feature, multinomial naive Bayes, works better than using the full word counts. And I want to note that for those of you who know about that there's an alternative version of naive Bayes called multivariate Bernoulli naive Bayes, using binarized Boolean features in multinomial naive Bayes is not the same as multivariate Bernoulli naive Bayes. In fact, multivariate Bernoulli naive Bayes doesn't seem to work as well for sentiment or other tasks. So we generally use binarized words rather than the full word counts. Although some researchers, like Rennie et al., have suggested that maybe something in between the frequency and just one word, like looking at the log of the frequency, which is smaller than the frequency, but maybe different than just using one, may be a useful thing to try. And if you're interested, you can read the literature on this whole question of which version of naive Bayes is most useful. As we introduced last time, Pang and Lee in our baseline classifier, we're going to use cross-validation. So cross-validation, remember, we break up our data into 10 folds. I've shown only 5 folds here. And inside each fold, let's say we might have the same number. Let's say we have half positive and half negative in our data. So we have, let's say, 4 positive and 4 negative in our test set. Then we're going to have also, let's say we have 500 positive and 500 negative in our training. So we're going to make sure that our test set has the same distribution of positive and negative as our training set. And then we're going to rotate our test set through our data. And each time we're going to train a classifier. So classifier 1, classifier 2 will train on this training data, test on this test data, and compute an accuracy. So we'll have accuracy 1, accuracy 2, accuracy 3 for each of these classifiers, and we'll compute these performances of these classifiers. So we'll have 5 different, or in our example here, 9 each time we're training on a fold and computing our accuracy. We'll take the average of all those, and we'll report the average of these 10 runs, each one training on 9 folds and testing on 1 test fold. So, and in general, it's nice if we also add a final test set. It turns out that other kind of classifiers, Maxent and SVM, often do better than naive Bayes. It depends a lot on your data set and the size of the data, but you'll want to take a look at all sorts of different classifiers when you're doing naive Bayes. Now, this baseline algorithm has a lot of problems. One problem is that sentiment is just a hard task in general. So here's some examples from Pang and Lee. Take a look at them. If you're reading this because it is your darling fragrance, please wear it at home exclusively and tape the windows shut. So that's a negative review of a perfume, but very hard to find just by using positive and negative words. Or the famous witty comment by Dorothy Parker on Katharine Hepburn: she runs the gamut of emotions from A to B. Again, quite difficult to detect. Another problem that often occurs in sentiment is called the thwarted expectation problem. It has to do with ordering effects. So here, read this first review. This film should be brilliant, sounds like a great plot, actors are first grade, lots of positive things going on, but at the end, the reviewer says it can't hold up. So, seems like a positive review, but it's not. Similarly, in the sentence, the very talented Lawrence Fishburne, not so good. So here we're setting up, I expected the movie to be good and it wasn't good. So this kind of ordering effect is something that we're going to have to deal with in any kind of more advanced sentiment algorithm. So that's the basic baseline algorithm that we can see for sentiment analysis.